Earth is a very unique planet in our solar system. It's the only known planet to sustain liquid water, the only known planet to have tectonic plates, the only planet in which its orbit is far enough to prevent being cooked by the sun, yet close enough not to freeze in the vast void of space. It is the only planet that we're aware of in the entire universe known to sustain life. But it wasn't always like this. Long ago, during Earth's infancy, it would have looked unrecognizable. Molten magma would be constantly spewing from volcanoes across the hardly formed surface, and meteorites would be crashing down constantly. The atmosphere would be completely toxic, primarily consisting of greenhouse gases such as methane and CO2, and most importantly, the entire planet was completely devoid of life. Of course, that will all soon change. As Earth cools off and recovers from its first hellish phase, it will soon enter its next chapter, the Archean Eon. Being the second eon of Earth's history and lasting from roughly 4 to 2.5 billion years ago, this officially marks the beginning of the geologic record as we know it. There's enough of a record, in fact, that we can divide this eon into 4 smaller eras, those being the Eoarchean, Paleoarchean, Mesoarchean, and Neoarchean. Throughout this installment, we'll make stops throughout each era and go over the notable events that may have happened by that time. From the arrival of the very first life forms to the actively moving continents, and soon the rise of oxygen in the atmosphere, sit back as we travel through 1.5 billion years of this journey's next chapter. Let's start somewhere within the Eoarchean, 3.8 billion years ago. Earth would have heavily cooled down at this point, though it was still considerably hotter than it is today. The late heavy bombardment, which would have started around the Hadean, came to a close around this time, and by this time Earth would have been completely smothered in oceans. The atmosphere would have still primarily been composed of methane and carbon dioxide, giving the atmosphere a rich orange color, and due to the atmosphere's lack of oxygen at the time, iron compounds would have dissolved into the water, making the early oceans green and much more acidic. As we dive deep into the ocean depths, we notice some hyperthermal vents, and upon closer inspection, microscopic levels to be precise, we can see things moving around. These small specks may have been the very first signs of life. But how did it get here exactly? Well, we're not quite sure. The topic regarding life's origin is still heavily debated and is currently going through extensive ongoing research. So far, the oldest uncontroversial date for the earliest record of life is about 3.5 billion years ago, early in the Paleoarchean. But there's evidence suggesting life might have appeared much earlier, perhaps as old as over 4 billion years within the Hadean. The most widely accepted hypothesis for the origin of life is a process known as abiogenesis, which, to put it as simply as I can, states that living things derived from non-living things. It's a fairly long process, with organic molecules progressively becoming more and more complex until it eventually becomes what we would consider an organism. Of course, this isn't the only explanation for how life came to be on this planet, as there's another, more out there theory. The panspermia theory suggests that life is carried throughout the universe via asteroids and comets, and crashed into inhabitable worlds such as early Earth to spread and prosper. It's been met with criticism, however, as it still doesn't exactly answer the question of how life came to be, instead just moving it to a different location. Like I mentioned, the origin of life is still a massive topic of discussion, and the true answer may forever be a mystery. Regardless of how and when it came to be, there's one thing that's for certain: life flourished in this new world. Fast forward 400 million years and we arrive in the Paleoarchean. Life has been evolving for at least 100 million years by now, and they've already begun to leave their mark. The oldest known fossils date to around this time, with such cases being strange structures known as Stromatolites, which I'll go more into detail later. At the time, all life consisted of prokaryotes, which today consist of bacteria and archaea. Unlike the more complex eukaryotes, which would evolve later, prokaryotes lacked major organelles such as the mitochondria or nucleus, and were generally much smaller. life would stay like this for at least another billion years, at least until evolution persists on. Zoom out to Earth as a whole, we notice that the world land masses are starting to become more apparent, and over millions of years appear to be slowly moving. This is one of the first instances of plate tectonics, which would have begun roughly 4 to 3 billion years ago. Of course, when exactly and how it came to be is still once again a mystery. As time goes on, more continental crust will rise up and eventually form what might have been the very first supercontinent, Vlabera. Forming around 3.6 billion years ago, it would have consisted of modern-day South Africa and parts of Australia. Another supercontinent, would have formed a little later in the Mesoarchean, some 3.1 billion years ago, and today would have consisted of places such as Africa, India, Australia, and more. It should be noted that despite technically being considered supercontinents, these continents wouldn't have actually been that big, perhaps being no bigger than modern-day Australia. Of course, as with many things, these continents are merely hypothetical, and whether or not they actually existed is still up to debate. Fast forward to 3 billion years from the present, and we've arrived in the Mesoarchean. Continents continue to migrate across Earth's surface as life forms continue to evolve and diversify. It's speculated that life might have begun to conquer the land at this point, though it would just be simple, single-cell bacteria for now. Looking over to the rocky shoreline, we notice those strange rocky structures I mentioned earlier, the Stromatolites. While they might seem like weird rocks at first, upon closer inspection reveals their true form. They're the result of single-celled organisms, which grow over and trap sediment in shallow waters, binding them to create small layers which pile up over time. Stromatolites usually grow to around a meter in height, although rare fossils show that they can grow to a whopping 6 meters, twice as tall as the average human. Despite being so ancient, these structures actually still exist today, albeit very rare and are only found in a few salty lagoons such as Shark Bay, Western Australia. As for the bacteria that create these structures, Cyanobacteria, they were quite different from what came before. They used a process of acquiring energy that was revolutionary, and which had ultimate long-term consequences on the entire planet. A process known as photosynthesis. In the modern day, photosynthesis is a process used mostly by plants, in addition to algae and some bacteria. It involves converting solar energy, in addition to CO2 and other molecules, into usable chemical energy, usually in the form of sugars. While exactly when and how it came to be is still unknown, fossil evidence places a good bet at around 3.4 billion years ago within the Paleoarchean. Back then, all life, including the cyanobacteria, would have been anaerobic. In other words, they can survive without the presence of oxygen. Anaerobic life still exists today, usually being secluded to areas such as the deep ocean floor, soil, and for some species, within your gut. Prior to photosynthesis, anaerobic life mostly relied on minerals present in the ocean in order to obtain energy. Back to the cyanobacteria, one thing to note is that during photosynthesis, they would have released a byproduct, one of which the world had never really seen before. A byproduct known as oxygen. It may not seem much at first, but in the long run, it's going to have dire, everlasting consequences on the entire planet and its inhabitants. But that story will be for another day. And so, we arrive at the end of this chapter, 2.5 billion years from the present in the Neo-Archean Eon. Enough continental crust is present to create the largest supercontinent yet, Kennerland, and both across its landscape and the surrounding seas, life continues to thrive while slowly altering the atmosphere's composition. All of these factors will eventually all come into play in the next installment, the Proterozoic Eon. Until then, I hope you enjoyed this video, and I'll see you next time.